This video is part of the lecture for multivariable calculus, and we are going to talk about arc length of a parametric curve. So let r of t be the position vector of a moving object. Then we take derivative of that and we say r prime of t. So if we have r of t like that, it's the parametrized curve in a space, then r prime of t would be a vector that is tangent to r of t. We use r prime of t for finding the tangent line to the curve, for finding velocity and acceleration. Velocity is actually derivative of r, and acceleration is the second derivative of r. And also we use r prime to find the length of arc, so arc length. But how do we do that? Well, we say that if we have r of t like that, we are going to make it into small sections like this. Some small segments like that, and each segment is something like this. At the time t, we are here, r of t. At the time t plus delta t, we are here. And then if we define s to be the distance traveled along the curve, let me move this sentence a little bit. Okay, so this part that we have in here between r of t and r of t plus delta t, it is delta s. Okay, now if r of t has coordinates x of t and y of t, and r of t plus delta t has the coordinates x of t plus delta t and y of t plus delta t. Okay, then when we move from r of t to r of t plus delta t, we have some changes in the x direction and some changes in y direction. So we're gonna have one delta x in here and a delta y in here, delta y. So I have a right triangle in here if I make a line in here. And I can do that. It's just because these segments are very small, so the arc would be approximately the length of this line. So I can call this delta s, and as you see, I have a right triangle. By Pythagorean theorem, I have delta s squared equals to delta x squared plus delta y squared. Pythagorean theorem. Then I'm gonna divide both sides of this, divide by delta t squared. So I get delta s divided by delta t squared equals to delta x divided by delta t squared plus delta y divided by delta t squared. As delta t goes to 0, which is basically r of t plus delta t is very close to r of t, so I have a very small segments, then delta s over delta t would be instantaneous rate of change that we call, which would be approximately square root of dx dt square plus dy dt square. Basically everything in here, everything in this equation would be instantaneous, and so I get this formula in here, which would be basically the speed, right? The length of the velocity vector. Very good. Why do we do that? It's just because, as I said, if we have a curve like this, we're gonna make it into very, very small segments as delta t goes to 0. So from t1 to t2, I make these small segments, and each of these segments, they look like this. That's why when I want to find the length of this parametric curve, a parametric curve from t1 to t2, I can say that L is the length of that. From t1 to t2, I sum all of these arc length, these small parts. When I want to sum it up, I use the integral ds dt, and then I'm gonna multiply it by dt so that I get the sum over all the ds. So you see. Now, if r of t has the components f of t, for example, for x, for y, g of t, and a function like h of t for z, if r of t has these components, then I would like to say that the integral from t1 to t2 would be the length of the velocity vector dt, which would be the integral from t1 to t2 square root of the first derivative of the first component square, derivative of the second component square, and derivative of the third component square. Okay, this is basically the formula that we use for finding the arc length of a parametric curve. Now let's look at some examples. I'm gonna look at the helix. So the helix has this parametric curve, cosine t, sine t, and then t. The question is, what is the arc length from t equals to 0 to t equals to pi? Okay, let me graph the helix very quickly. So actually, this is x-axis, this is y-axis, and then this is the z-axis. As you see that the helix lies on a cylinder of radius 1, it's just because this is the x component, this is the y component, this is the z component, and I know that sine squared plus cosine squared is equal to 1. That's why I get a cylinder, and I have a cylinder in here. Let me graph the cylinder. That looks like this. And at t equals to 0, I'm at this point because cosine of 0 is 1, sine of 0 is 0, and then 0. So at t equals to 0, I'm at the point 1, 0, 0. And then the curve starts going up, but it moves around this cylinder. Okay, it moves like this, and at t equals to 0, it's here. At t equals to pi, cosine of pi, so let me basically write this. R of 0 is 1, 0, 0. r of pi, plug in pi, cosine of pi is -1, sine of pi is 0, and then pi. And so -1, 0, and pi. So x would be -1 somewhere in here. Yeah, at t equals to pi. Okay, so what is the arc length? All I need to do is to find the velocity. Velocity is r prime of t, which is negative sine t cosine t and 1. And I need to find the speed, which is the length of the velocity, square root of negative sine t squared plus cosine t squared plus 1 squared. Sine squared plus cosine squared is equal to 1. I have another 1, so it is square root of 2. So the arc length from t equals to 0 to t equals to pi is equal to the integral from 0 to pi of square root of 2 dt, which would be root 2t from 0 to pi, would be square root of 2 times pi. Okay, this is the length of this arc in here. Okay, look at example 2. Example 2, what is the arc length of this parametric curve? X equals to cosine t, y is equal to sine t from 0 to 2 pi. Okay, what is this curve if I want to graph it? Okay, x-axis, y-axis, and this curve is sine squared plus cosine squared is equal to 1, so it's a circle of radius 1. From 0 to 2 pi, at 0, plug in 0, I get 1 and 0, so I'm here at t equals to 0, and then plug in pi, -1, 0, so at t equals to pi we're here, and then at t equals to 2 pi still here, so it moves along this circle one time and it goes back to the beginning point. So L would be the integral from 0 to 2 pi of the speed dt, so 0 to 2 pi square root of derivative of cosine is negative sine square, and then derivative of sine, I need to find the speed, right? So I need to differentiate the curve. So derivative of sine is cosine. Basically, I just skip one step, dt. So this is equal to 1. What do you think about the arc length? It's a circumference of a circle, right? So I expect to get 2 pi dt, which would be t from 0 to 2 pi is equal to 2 pi. Perfect. And the next question is, what is the arc length of x equal to cosine of 2t, y equals to sine of 2t on t between 0 and 2 pi? Okay, well, this is the same case. It's just because I have a cosine square plus sine square and is equal to 1. That's why I get a circle of radius 1. But if I look at that, if I plug in 0, I get 1 and 0. So at t equals to 0 in here, if I plug in pi over 2, I get cosine of 2 times pi over 2, which would be cosine of pi, -1, and then sine of pi, 0. So at t equals to pi over 2, I'm here. At t equals to pi, plug in pi, I get 1 and 0 here. So as you see that from 0 to pi, We just move along the around the circle one time. So after pi, I go to 3 pi over 2 and I go to 2 pi. So it moves along the circle twice. If you pay attention to that. But what do you think about the arc length? What do you expect to get? It should be twice as the first one, right? So let's check. Let me find the velocity this time. So the velocity derivative of cosine would be negative 2 sine of 2t and then 2 cosine of 2t. So L is the integral from 0 to 2 pi of the speed dt, which would be 0 to 2 pi square root of negative 2 sine of 2t square plus 2 cosine of 2t square and then dt. So I get what? I get 4 sine square of 2t. Here I get 4 cosine square of 2t. So if I factor out the 4, I get sine square plus cosine square, which is 1. So the integral from 0 to 2 pi square root of 4 dt, which would be 0 to 2, which would be the integral of 2, which is 2t from 0 to 2 pi 4 pi. Okay, as we expected. Okay, let me give you just one small note. Sometimes we are given, what if the curve is not parametric? So we are given not a parametric curve. We are given something like that, y equals to f of x, for example. And to do that, something that I recommend is to parameterize that. How? I'm going to parameterize it like that. I'm going to let x to be t and y to be f of t. And so it is t and f of t. Okay? Now, the same as usual, L, use the same formula from t1 to t2. For example, the arc length would be square root of the speed, derivative of that 1 and f prime of t. So it would be 1 square plus f prime of t square dt. Or something that is very common to write from for example, any point A to the point B, 1 plus dy dx square dx. Since if I have x-axis, y-axis, if I have a curve like that, y equals to f of x, it's not a very good curve. Like this, f of x from A to B, this is your arc length. If you parameterize that, you have from t1 to t2. If you don't parameterize it and you want to use this formula, it's from A to B and it's the arc length.